Hello, everybody, and welcome. It is 2023, December 19th, and it is currently 12 p.m. Pacific Standard Time. My name is the Shy Hat, and we're here to do day 19 of our Advent of Cyber event, which is going on at TryHackMe.com. All right, so if you want to participate in these challenges, you can do so at the following link that I'm going to be putting in the chat below. So this is an event that runs from the 1st of December until the 24th of December, with every day being a different beginner-friendly cybersecurity challenge for us to solve. So it's a great way to be introduced to a lot of different topics in cybersecurity in a very hand-holdy, guided format. All right, so we're going to dive right into our challenge today. It is day 19, and the first thing we need to do is we need to click on this button right here, which is Start Machine, and that's going to start the virtual machine that we're going to be using in today's exercise. So it's going to take a little while to initialize over here. So while we're waiting for this virtual machine to initialize, we're going to take a look at what we're going to be learning today. So today's objectives. So the elves are hard at work inside Santa's Security Operations Center, the SSOC, looking into more information about the insider threat. While analyzing the network traffic, Log McBlue discovers some suspicious traffic coming from one of the Linux database servers. Quick to act, Forensic McBlue creates a memory dump of the Linux server along with the Linux profile in order to start the investigation. So what are we learning today? We're going to learn to understand what memory forensics is and how to use it in a digital forensics investigation. We're going to understand what volatile data and memory dumps are. We're going to learn about volatility and how it can be used to analyze a memory dump. And we're going to learn about volatility profiles. All right, so the first thing we need to learn is what is memory forensics. Memory forensics, also known as volatile memory analysis or random access memory forensics, is a branch of digital forensics. It involves the examination and analysis of a computer's volatile memory, otherwise known as RAM, to uncover digital evidence and artifacts related to computer security incidents, cybercrimes, and other forensics investigations. This differs from hard disk forensics, where all files on a disk can be recovered and then studied. Memory forensics focuses on the programs that were running when the memory dump was created. This type of data is volatile because it will be deleted when the computer is turned off. So let's take a look at what is volatile data. In computer forensics, volatile data refers to the information that is temporarily stored in a computer's memory and can be easily lost or altered when the computer is powered off or restarted. Volatile data is crucial for digital investigators because it provides a snapshot of the computer state at the time of the incident. Any incident responder should be aware what volatile data is. The reason is that when looking into a device that has been compromised, an initial reaction might be to turn off the device to contain the threat. Some examples of volatile data are running processes, network connections, and RAM contents. Volatile data is not written to disk and is constantly changing in memory. The issue here is that any malware will be running in memory, meaning that any network connections and running processes that spawn from the malware will be lost. Powering down the device means valuable evidence will be destroyed. All right, so everybody, before we proceed any further, we see that our virtual machine for today's challenge has spun up and has finished initializing. So what we need to do is we're going to put this virtual machine in its own web browser tab so that we can better take a look at what's going on when we interact with it. So what we can do is we can click on this button right here, which is labeled View in Full Screen. So we're going to click on that, and that's going to put the virtual machine in its own web browser tab. Okay, so that done, we can go back to our original web page, and then we can close out this part of the web browser pane by clicking on this button at the bottom here, which is labeled Exit Split View. So we click on that, and now we can see that we can see the web page in full screen again, which is beneficial when we're trying to look at what we're trying to read. All right, so what we're looking at. Okay, so next we're going to cover what is a memory dump. A memory dump is a snapshot of memory that has been captured to perform memory analysis. It will contain data relating to running processes captured when the memory dump was created. What are the benefits of memory forensics? Memory forensics offers valuable benefits in digital investigations by capturing real-time data from a computer's volatile memory. It provides rapid insight into ongoing activities, detects stealthy threats, captures volatile data like passwords, and allows investigators to understand user actions and system states during incidents, all without altering the target system. In other words, memory forensics helps confirm malicious actors' activities by analyzing a computer system's volatile memory to uncover evidence of unauthorized or malicious actions. It provides crucial insights into the attacker's tactics, techniques, and potential indicators of compromise. Another thing to keep in mind is that capturing a hard disk image of a device can be time-consuming. Then you have to consider the problem of transferring the image, which could be hundreds of gigabytes in size, and that's before you even consider how long the analysis will take the incident response team. This is where memory analysis can really help the IR team. Capturing a memory dump from any device will be much faster and smaller. Suppose we prioritize RAM over a hard disk image. In that case, the IR team can already start analyzing the memory dumps for IOCs while beginning the process of capturing an image of the hard drive. Okay, next we're going to talk about what processes are. A process is an independent, self-contained unit of execution within an operating system that consists of its own program code, data, memory space, and system resources. Imagine your computer as a busy chef in a kitchen. The chef can cook multiple dishes simultaneously, but to keep things organized, they use separate cooking stations for different tasks. Each cooking station has its own ingredients, pots, and pans. These cooking stations represent what we call processes in a computer. This is crucial in memory forensics because knowing the processes that were running during the capture of a memory dump will tell us what programs were also running at that time. We can categorize processes into two distinct groups. User processes, which are processes that a user has started. They typically involve applications and software users. They typically involve applications and software users interact with directly. As an example, Firefox. This is a web browser that we can use to surf the web. And the other category is background processes. These are processes that operate without direct user interaction. They often perform tasks that are essential for the system's operation or for providing services to user processes. As an example, automated backups. Backup software often runs in the background, periodically backing up data to ensure its safety and recoverability. Okay, so this section on connecting to the machine we can skip. And now we're going to talk about volatility. This is the software we're going to be using in today's exercise. Volatility is a command line tool that lets digital forensics and incident response teams analyze a memory dump in order to perform memory analysis. Volatility is written in Python, and it can analyze snapshots taken from Linux, Mac OS, and Windows. Volatility has a wide range of use cases, including the following. Listing any active and closed network connections. Listing devices running processes at the time of capture. Listing possible command line history values. Extracting possible malicious processes for further analysis. And the list keeps going. For this task, we'll examine the memory dump of a Linux device. For your convenience, volatility is already installed on the VM. We can look at different help options using vol.py-h. Okay, so if we copy this command And what we're going to do is we're going to open the terminal window inside of our virtual machine. So we're going to go to the tab which has our virtual machine here, and we're going to open up a terminal with this shortcut button, or this shortcut button. So I'm going to click on this one, and then I'm going to make the terminal nice and big for us to see, and then I'm going to paste in this command that I copied from the web page. So this is going to give us a bit of information about the volatility program. Okay, so we can see all sorts of different, let me make this a little bit wider. So this gives us all sorts of different help text for the volatility program. Let's keep on going. I'm going to clear the screen. And then we're going to go back to the web page for further instructions. At the time of writing, there are two versions of volatility. Volatility 2, which is built using Python 2, and Volatility 3, which uses Python 3. There are different use cases for each version, and depending on this, you might choose to use one over the other. For example, Volatility 2 has been around for longer, so in some cases, it will have modules and plugins that have yet to be adapted to Volatility 3. For the purposes of this task, we're using Volatility 2. Before we start analyzing the memory dump, let's go into what profiles are and how volatility uses them. So, volatility profiles. Profiles are crucial for correctly interpreting the memory dump for a target system. A profile in volatility defines the operating system's architecture, version, and various memory specific to the target system. Using the appropriate profile is crucial because different operating systems and versions have different memory layouts and data structures. Volatility comes with many profiles for the Windows operating system, and we can verify this using vol.py --info. Okay, so we're going to skip this one, and we're just going to believe what is on the page here. Did you notice that there aren't any Linux profiles listed? Profiles for the Linux operating system have to be manually created from the same device the memory dump is from. Here are some of the reasons why we typically have to create our own Linux profile. Linux is not a single monolithic operating system, but rather a diverse ecosystem with many distributions and configurations. Each distribution may have different kernel versions, configurations, and memory layouts. This variability makes it challenging to create a one-size-fits-all profile for Linux. Unlike Windows, which has more standardized memory structures and system APIs, Linux kernels' internals can vary significantly across different distributions and versions. This lack of standardization makes it difficult to create generic Linux profiles. Linux is open source, meaning its source code is readily available for inspection and modification. This leads to greater flexibility and customization, but also results in more variability in memory structures. Creating profiles is out of scope for this room. So for your convenience, a profile is already in the home Ubuntu desktop evidence directory called Ubuntu, this file name right here. To use the profile, we have to copy it where volatility stores the various profiles for Linux. This command right here will take care of it for us. Then run here to confirm that our profile is set. So what we're going to do is we're going to copy this command over here. So copy that, and then inside a virtual machine, we're going to paste it in and run the command. Okay, what we need to do is we need to go to the relevant directory first. So cd desktop, cd home slash, wait, let me get the directory again. So it's cd home desktop evidence. Okay, so cd tilde / desktop / evidence. Okay, and then we're going to paste in the command that we copied from the web page and run that. And then we're going to run this command right here to double check that we have the profile loaded in. So we're going to copy and paste that. Remember that paste inside the terminal window is Control-Shift-V. Okay, so we see that the Linux Ubuntu profile is here. So that's what we need to do. If you're curious about how to create a Linux profile, you can read this article right here. Okay, now we can begin our analysis. So memory analysis. The file linux.mem contains the memory dump of the Linux server we're going to analyze. This file is located in our home directory. For volatility to begin the analysis, we need to specify the file with the -f flag and the profile with the -- profile flag. We can use the -h flag to look at all the different plugins we can use to help with our analysis. Okay, so this is an example of the help flag to see all the plugins we can use with this particular profile, but we don't need to pay too much attention to that right now. So we're going to talk about some volatility plugins. So we're looking at the history file right now. The history file is a good place to start because it allows us to see whether there are any commands executed by our malicious actor while they're on the system. To examine the history file for any such commands, we can use the Linux bash plugin. The command will take a little bit less than a minute to finish executing. Okay, so here we're going to run this command right up until here, copy that, and this is going to see what commands were run while inside of the terminal. Okay, paste that in and then run it. So this might take a little bit of time to execute, depending on the speed of the virtual machine that we spun up. So while we're waiting for this, let's take a look at the web page and see what's going on. When performing a cross-reference check with the ELF analyst who was using the server, we can identify the following suspicious commands. Okay, number 1, the MySQL-U root -p redacted command was used by the ELF analyst, but the cat/home/elfie.bash history command was not. This means that the malicious actor most likely saw the MySQL command and had access to the database. There's a lot of sensitive information about the merger and the pipelines that the malicious actor could have gained access to. Okay, so let's take a look at whether or not the virtual machine has finished running this. Okay, so here we see that one of the commands that was run was MySQL as user root using this password. So you should copy this password right here because it's going to be one of the answers for the questions we're going to answer later. So please copy that because we're going to be using that later. Okay, number 2, we can identify the curl HTTP, this IP address toy miner, ominer command, which the ELF analyst confirms that they didn't use themselves. This tells us that a malicious actor used curl to download the toy miner file and saved it using the -o parameter as a file named miner. We can also see that the malicious actor executed the miner file using the /miner command. Now that we understand what the malicious actor executed, we can look into the system's running processes. So let's take a look at these two commands right here, this curl command and this // command, and try to find it inside of this output over here. So the curl command is right here, and the // command for the miner is right here. All right, so now that we understand what the malicious actor executed, we can look at the system's running processes. In memory forensics, examining running processes is a fundamental and crucial part of analyzing a system's memory dump. Analyzing running processes in memory forensics can be highly effective in identifying anomalies because it provides a baseline for what should be expected in a healthy and normal system. For example, we know that the miner program was executed, so let's see what the process looks like. To examine the running processes on a system, we can use the Linux underscore pslist plugin. Okay, so we have this command right here, which we can copy. Okay, and so at the end we see Linux underscore pslist. So copy this command and then run it in the virtual machine. And this might take a little time to run. Okay. All right, so this this output is a little bit garbled, so I'm going to make the window slightly smaller and slightly longer, and then hopefully we can see the output a little better. Let me make this a little bigger too. So here up at the top, we see the offset, okay, the name of the process ID, the process parent ID, and the user ID, and some other stuff right here. To see what these things actually mean, let's take a look back at the web page. So as you can see, this plugin doesn't just list each process's name. It also lists the process ID and the parent process ID. This helps determine what is often referred to as a parent-child relationship between processes. There are only two anomalies we can quickly identify. Number one, the ELF analyst confirmed that they didn't execute the miner process. Based on the program's name, our initial assumption is that we may be dealing with a crypto miner. A crypto miner, short for cryptocurrency miner, is a computer program or hardware device used to mine cryptocurrencies. Cryptocurrencies are digital or virtual currencies that use cryptographic techniques to secure and verify transactions on a decentralized network called a blockchain. Our insider threat could be trying to use our Linux server to mine cryptocurrencies and to make some extra ELF bucks. Number two, the MySQL server appears to be benign, but this is misleading. The real process for MySQL is called MySQL-D, as listed above. The ELF analyst confirmed that they didn't execute this. Given that the PID of this process is different from the PPID of the miner process, this process did not spawn from the miner directly. We would like to know more about these processes. A good way to do this is by examining the binary of each process. We can do this via process extraction. A good way to understand what a process is doing is by extracting the binary of the process. This will help us analyze its behavior using malware analysis. We also want to extract the binary of the process as a form of evidence preservation. To extract the binary of a process for examination, we can utilize the Linux procdump plugin. We just need to create a directory to indicate where we would like to extract, where we'd like the extracted process to go to with the makedir extracted command. Then we utilize the -d flag to tell volatility where to place the extracted binary and indicate the process's PID with a -p flag. Creating a separate directory doesn't just help us stay organized. It's required by volatility in order to avoid errors. Based on our file history and running processes findings, we are now going to extract the miner and MySQL binaries using the command shown below. Okay, so first what we need to do is we need to create a directory called extracted to put the binaries into. So we copy this command right here, and then let me get down to the bottom, and I'm going to adjust the size a little bit. And then I'm going to clear this screen, and then I'm going to run this command right here to create the directory called extracted. Okay, that done, we can then run this command right here for the procdump command. Okay, so right here, we're going to run this command, except that the -p flag here says PID. But what we need to do is we need to supplied the command with the process ID of, I think this one is for the miner program. So we're going to delete PID, and then we're going to look up what the process ID of the miner command is. Let me get that from the previous command, which was this one, the PS list. So we should see that the miner command should have a process ID. It is this one right here. So the process ID is 10280. We should remember this because it's one of the questions that we're going to answer later, and we're also going to need to plug this into a bunch of different commands. So 10280. So let me copy the command again. So right here, we're going to copy this. We're going to paste it in. And then for the PID, we're going to do 10280. Okay, and what this is going to do is it's going to extract the processes. It's going to extract the process, and it's going to put the binary inside of the extracted directory that we created. So we run this. Running. And then inside the extracted directory, it created a file called miner.this.this, okay? And we're going to repeat the process for the MySQL binary. So what we can do is we can just copy this command right here. So this is the command we used previously, and we can just copy this command directly to extract the MySQL binary and put it in the extracted directory. So we're going to paste it in and then just press enter. Okay, so after that's done, we'll have both the miner binary and the MySQL server binary inside the extracted directory, and we can proceed. We have successfully extracted the suspicious programs into the extracted folder. Having heard all the commotion, McSkitty offers to help with the investigation by taking over the operation's threat intelligence tasks. McSkitty needs an MD5 hash of each extracted binary, which we can provide with the following command. Okay, so what we need to do is we need to get the MD5 sum of the MD5 checksum of each one of these files, and we can do that by running the following two commands. Okay, so we're going to copy this one. We're going to paste this in, but the PID hasn't been provided to us, so we have to put it in ourselves. So remember, it's 10280. Okay, we run that, and this is the MD5 sum of the miner program. Okay, you're going to want to copy this because we're going to use this to answer one of the questions later. And we also need to get the MD5 sum for the second file, which is this one right here, which is this command right here. We can copy that, and then we can run it. And this is the MD5 sum for the MySQL binary program. So remember to copy this one too, because we're going to use this as one of our answers. In the meantime, remembering what he learned from the Linux forensics room, Forensic McBlue wants to check for persistence mechanisms that may have been planted by a malicious actor or crypto miner. Persistence mechanisms are ways a program can survive after a system reboot. This helps malware authors retain their access to a system, even if it's rebooted. Good old McBlue remembers that a common persistence tactic is via cron jobs. While there isn't a plugin to review cron jobs, we can review them by enumerating for cron files. So we're going to do file extraction. As stated above, we want to look for any cron files that may have been placed by malicious actors or crypto miners. This can help us identify if there are any persistence mechanisms at play. For example, is the MySQL server process For example, is the MySQL Server process we found before part of the persistence mechanism? But how can we enumerate files on the server? We can utilize the Linux Enumerate Files plugin to help with this. The benefit of this plugin is to help us review any files of interest. The plugin's output will be too large, so we can utilize the grep utility to help us focus our search. Okay, so what we can do here is we're going to copy this command right here, which is going to enumerate the file, and then inside of the file we're going to grep for this string right here, which is cron. All right, so I'm going to clear this so we can see the output near the top of the screen. I'm going to copy the file. Sorry, I didn't copy the command correctly. Let me do that again. Okay, I'm going to copy this, and then I'm going to paste it in. And this might take a little time to run, but while we're waiting for that to run, let's go and see what is up with this. So we can quickly identify the cron tab located in this particular directory, var spool cron tabs elfie. We speak to the elf analysis, who confirms that they didn't have any cron jobs set up on this server. We can now extract the file by selecting the inode value, the hex-like value located to the left of the file name, and using the -o option to name our file during output. Okay, so we go back to the virtual machine, and it's taking quite a while to run. Okay, so let's wait on that. Okay, the next command we want to run is this command right here, which is going to find this file at this particular address, memory address right here, and it's going to output the file as a file called elfie. Okay, so before we run this command, let's take a look and see if our virtual machine has finished running the previous command. Okay, so which cron output are we paying attention to here? Let's look back here. We quickly identify the cron tab located at var spool cron tabs elfie. Okay, so this one right here, let's see if we can find it. And okay, it's right here. Okay, and this is the address that we use for the following command. Okay, all right. So let's paste that command in. Okay, let's copy the command again. All right. So we copy the command again, and then paste it in. And so what we're doing here is we're going to grab this file right here, which is at this memory address, and we're going to output it as this file called elfie. Okay, so we run the command, and let's take a look at the web page to see what's going on next. Go ahead and examine the contents of the elfie file using the cat elfie command in order to understand how the MySQL Server process was placed. Okay, so that's what we're going to do. It's finished outputting the file to the file called elfie. If we ls inside of this directory, we see that the elfie file is here. We can read the file with cat elfie. And we can see here that it starts up a binary right here, which is MySQL Server, from the var temp, this hidden file right here as a directory, and then MySQL Server. All right, so we're gonna have to remember this as well, because we're going to use this file path right here as one of the answers for our questions. Okay, so before we finish off the room, let's take a look at the conclusion. With all the overwhelming evidence, Elf McBlue decides to move the incident following the company, incident response, and incident management process. Given the nature of the incident threat, along with the current news of the acquisition, the next question that arises from the incident is, are all the pipelines safe? Okay, so that's kind of a hint as to what the next task is going to be. But before we finish off today's exercise, let's answer the questions for the exercise. So the first question is, what is the exposed password that we find from the bash history output? All right, so if you remember to copy the password when we were running our commands, it was this one right here, and we submit that as an answer. What is the process ID of the miner process that we find? Okay, so if you remember, it is 10280. What is the MD hash of the miner process? Okay, so if you remember to copy down the MD5 hash when we ran that command, it's this right here, and we submit that. And then we also need to provide the MD5 hash of the MySQL Server process, which is this one right here. Okay, use the command strings extracted / miner PID, okay, and this offset right here, and grep for HTTP : // so the miner binary file, we're going to try to find a HTTP URL from that file. So what we're going to do is we're going to copy this command right here, and then we're going to go to our virtual machine. We're going to paste in this, but remember, the PID is not here. So what we need to do is provide the PID for the miner, which if you remember is 10280. And then we run that command. Okay, and then we find this URL right here. This is the URL we're looking for right here. McGreedy secret c2.thm. So we can copy this, but the question asks for us to fully defang the URL using CyberChef. Okay, so what we can do in Google, you can search for CyberChef, which is a website that lets you do all sorts of great things with encryption and encoding and stuff like that. So we can click on the first result in the Google search here. That leads us to the CyberChef website here. Okay, what we can do inside of the operations window over here is you can search for defang. So we're looking for defang URL, and then we're going to drag this over to the recipe, and then we're going to, in the input window over here, we're going to paste in the URL that we got from the file, which is this one right here. And the output is going to be the defanged or the unclickable version of the URL. So what we do is we copy the URL from the output, and then we're going to provide this as the answer for our question. Okay, so back up the web page, paste this in, submit. And the last question is, after reading the Elfie file, what location is the MySQL Server process dropped in on the file system? So we can go back to our virtual machine and scroll up a little bit, and we see that it is this directory right here. We can copy it, and then we can supply this as the answer to our question. Okay, and that's the end of this room. There is another room associated with memory forensics on TryHackMe, which is the volatility room, which you can find here. But everybody, thanks for coming to watch this this live walkthrough of the TryHackMe Advent of Cyber 2023 Day 19 challenge. My name is TryHack, and we'll be back tomorrow to solve day 20. Thank you very much for watching, but until then, have a great day, and we will see you next time.